Hi, I'm Anthony Beck. My presentation is on, I'm sure I left it somewhere, discovering our heritage through aerial prospection. So, what are we trying to detect?
Here is an example of buried archaeological features. We have a ditch feature, post hole, and a wall. So both a ditch and a post hole are infilled with different sedimentary sequences depending upon their formation process and deformation process, and the wall itself obviously is still a reasonably intact barrier. These are all within a plough zone, so you've got the plough which is diffusing the sediments here and spreading the stones and brick from the wall, but you also have an occupation horizon here, which is providing slightly different soils to the background soil matrix. So obviously we can detect these just by looking at the soils. There's differences in the soil matrix because you have mixing here from the ditch sediments with the natural soil. You have your differences between your anthropogenic soil and the natural, and again you're going to have larger clasts come in with the wall. The one that we can't see is a post hole because it's too small a feature for us to observe. But we can also see them as a topographic effect. With the sun low in the sky somewhere over here, you'll see sun rays come down and produce a shadow mark here or a highlight on what would be quite ephemeral topographic features in that landscape. In addition, you can see variations in crop, and crop as a proxy evidence. And this is one of the major ways of locating subsurface archaeology. And so under the right conditions, where you can see either crop stress here of the wall, where you have differences in root penetration and nutrient uptake, or vigor here over the ditch, which is it's hypothesized is acting as a kind of oasis for both nutrients and water, so in periods of drought it has a relatively vigorous crop. And this is expressed either as a change in crop canopy height or in crop colour. And the sensitivities of either crop stress and vigor are expressed in the visual part of the electromagnetic spectrum, but also in the parts that we can't see in the non-visual components. Thank you.
Okay, so we've had a nice summary of how things are displayed. So we can see that archaeological sites can show up as structures, shadow marks, soil marks, crop marks. There's also thermal anomalies. But all of these different contrasts are influenced by localized effects. So there's weather, season, the soil type and soil moisture, and the different crop types. Generally, the important points for site detection are that archaeological sites are physical and chemical phenomena. They consist of different kinds of constituents, which means that they show contrasts in different ways. The abundance and distribution of these constituents vary, both within sites and between sites, and these attributes may be masked or accentuated by a variety of other phenomena. In essence, discovery requires the detection of one or more of these site constituents, which is sufficient enough to suggest that a site may be present. So, what do we use to detect any archaeology? And there's a number of different platforms we can use. There's satellite, aerial, near ground, photography from kites, blimps and microlights, and then ground, traditional geophysics. For the purposes of this presentation, we'll be focusing on aerial. And traditional aerial photography has been really the most successful detection technique. It's a low-level platform using handheld cameras, digital SLRs, traditional SLRs. There's a reliance on oblique photography, which means also that it's focusing on the optical and near-infrared wavelengths, and it's been used continuously since the early 1900s. However, it's reliant on specific seasonal and environmental conditions, and because it's been flown for such a long time, we need increasingly extreme conditions to detect new sites. There's a low understanding of the physical processes outplay outside the visual wavelengths. We've got a reasonable understanding of what goes on visually, but there's also significant bias in its application. In the environments where it's productive, it's used a lot, but in areas such as clay, where it tends not to be responsive, it's not flown very often. The surveys themselves don't tend to be systematic. Photographs are taken by an observer from what the observer sees. So if the person in the plane can't see the feature, it's not flown, it's not surveyed. Any interpretation tends to be more art than science. And here's an example of an aerial photograph over one of our sites. As you can see in here, I have a whole range of interesting features and structures. Okay. So, as part of the electromagnetic spectrum, where does traditional aerial photography work? Looking mainly in the visual part, but if you go to the full electromagnetic spectrum, it is very big. This is logarithmic scale, so the visible component is really just a tiny area of the whole spectrum. What can we do if we start to exploit more of that spectrum? Well, we can use multi or hyperspectral imaging. These offer a greater opportunity to detect archaeological phenomena, and many of the contrasts that we see are easy to identify in non-visual wavelengths. So if looking at expressing soil mineralogy, moisture and temperature, all of these can be seen outside the visual. And this has a number of benefits. We can potentially extend the window of opportunity for archaeological identification. Crop marks, for example, are quite ephemeral features that have a short duration. We may not therefore require the extreme environmental conditions which we're now needing to pick up new sites. Most importantly, it may be applicable in non-responsive environments. So, what do we do about this? We can go back to first principles. We've already known that detection requires the identification of a physical, chemical or biological contrast. We also need to deploy that sensor under favourable conditions so we can detect that contrast. And it's the contrast detection which is the most important things. Then it's the timing. When are we detecting it? Are the contrasts permanent or transitory? We don't really know. Well, we do know in some instances, but we don't have a good understanding of the whole dynamics and the whole process. So we need to get a handle on all of these processes associated with detection. Primarily, we need to get a better understanding about the resolution. And resolution falls into four strands. There's the spatial resolution. It needs to have a fine enough spatial resolution so we can actually observe the object we're interested in. All of these images here refer to the same area, and as you can see, we can't see very much in Landsat for these field boundary walls, although you can detect these soil marks from tells. You need appropriate radiometric resolution. Now, radiometric resolution refers to how fine the system can represent measurements. And a good analogy of this is measuring height. It's difficult to detect a small change in a child when they're growing if the ruler you're using only measures to the nearest metre. We need to make sure that we have a measuring device that measures a centimetre at least. And so radiometric resolution refers to that refinement in the measuring parameters. Temporal resolution, we need to know when to look for the difference. Here we're looking at thermal contrasts throughout the day. So if we were taking measurements at just after 8 o'clock, there is no difference between the water and the soil. However, if we're taking our measurements just after solar noon, we see the maximum contrast. So we can have a problem of now you see me, now you don't. And then spectral resolution. We need to know which parts of the electromagnetic spectrum contain the contrasts that we want to see.
This video is about spectral resolution. As you can see here, we have a single band image, black and white, panchromatic, but for the purposes of this we'll call it monospectral. It's broken up into a number of different regions. It's got pinewood, grassland, some red sand and silty water. And each of these has a reflectance index here. This would be classed as their spectral signature. So we're looking at the amount of reflectance coming from the sun and the wavelength on which it occurs. Now, as it's a single band, we're looking at one broad capture across broad wavelength, and we have this spectral response. So, it's quite easy to discriminate the red sandpit here because it reflects very highly, but the other three have pretty similar reflectance percentages. Now, when we move into the multispectral, here we're looking at 4 bands from Landsat. We can see that we actually have a layer stack of multiple single band images, and you notice here that we now have a spectral curve where it's easier to discriminate things, so we can do some band algorithms and band mathematics to start to discriminate some more of these features more effectively. You'll also notice that this spectral curve is starting to become a little bit more unique. Here we can understand, or differentiate rather, what was going on with these 3 different types. We now see that we're getting more variation, and we can find different ways to discriminate between them, particularly looking at, say, ratioing between band 4 and band 3, for example, and that would be your red edge shift, looking at vegetation. Now if we pull into hyperspectral, and here we're looking at avarice, which has many hundreds of bands, you're looking at a very complex spectral signature, which allows you to discriminate quite finely about what the object under study actually is. You have a huge cube of information, and here you have an excess data problem. You've got lots and lots of data across a large spectral wavelength, which allows you to discriminate in quite a refined way about what's going on within that scene. In addition, you can get lab-based spectral signature curves, which you can compare against what you're getting in the field, and define elements down to either specific vegetation species or specific types of geology.
Okay, so we have a good body of, a good theoretical basis to use spectral approaches to detect archaeology. However, there are issues here, as archaeology doesn't produce unique spectral signatures. From work that was done in Syria, we noticed that you're seeing a perturbation or change in localized matrix. So you're seeing generally the same soil types, but a change in its structure, which is giving a slightly brighter reflectance. And we would argue that this happens with every form of archaeological matrix. So rather, we're looking at localized disruptions to a matrix. And the nature of these disruptions vary and includes changes to soil structure, changes to moisture retention capacity, changes in geochemistry, magnetic or acoustic properties, and changes to topography. Many of the things that we talked about earlier on. At least one of these distributions will produce a contrast which is detectable. The challenge for us is to know what sensor to use, how sensitive that sensor needs to be, and when to deploy it. Okay, so what we're going to do is to look at a range of different ground observation benchmarking. And we're going to do that based upon an understanding of the nature of the archaeology itself, what it's made of, what surrounding materials are, and what's growing on top of it. What are the proxy materials, in this instance crop? The sensor characteristics, the spatial, spectral, radiometric and temporal, again as we've already discussed, and the environmental characteristics, which are a range of complex natural and cultural variables that can change very rapidly over time. So trying to understand this periodicity of change will require intensive ground observation. And that's what we're doing with the DART project. We have 2 sites we're looking at, located in Diddington in Cambridgeshire and Harn Hill in Gloucestershire, both with contrasting clay and well-draining soils. Each has an identifiable archaeological repertoire, and both are under arable cultivation. Interestingly, both of them have contrasting macro-environmental characteristics. Diddington is drier and warmer, and Harn Hill is wetter and slightly colder. And we're going to run a whole range of different measurements over a 14-month period. So it's spectradiometry, which is essentially a spectral camera, where we'll be looking at soil and vegetation every month, and when the crop is growing, we'll be going back every 2 weeks to Diddington. We'll be looking at crop height. We'll be using Flash Res 64, which is a resistivity device, and we'll also be inducing events there to look at changes, putting water on the sites, traditional resistivity devices, ground penetrating radar. We'll be embedding soil moisture and temperature probes, and they'll be logging approximately every hour, and each site will have a weather station associated with it. So we're looking at some results from spectradiometry. This is broadly how the Flash Res 64 works, so we can take a whole range of readings across these different probes. And this is an example of how the probes will be embedded, so we'll have good coverage within the feature and outside to pick up lateral drop-off. In addition, we'll be undertaking a battery of lab measurements, including geotechnical and geochemical analyses. So that'll provide the background with which we can start to understand the measurements that are coming from the field. Now, in Cambridgeshire, this spring has been dry since 1910 and is to provide exceptional conditions. We put in an application to NERC to fly their Eagle and Hawk hyperspectral sensors, which they agreed to. And so we have 256 bands over a 3 km² area. And this is a huge amount of data. The problem or the challenge we have at the moment is how we get information out of this. We can use brute force statistics, for example, principal components analysis, and this is really starting to show the correlations between each of the different bands that we're getting. This may kind of show that we're getting a change, but not necessarily why we're getting a change. We can also look at the theoretical understanding about light interaction, how light interacts with plants and soils, how this changes into different stress conditions, be it nutrient or drought, and how this changes over time. And here we have a good example of a number of different wavelength ratios which should show crop stress. And so here's one from Verhoeven and Dunius, 700-800 ratio, Carter and Miller, and Carter. So you can see each of these ratios is bringing out the structure in the archaeological features. And we can do this by empirical observation. And here we're comparing the spectroradiometry, and we can look at issues of scale, illumination geometry, and pixel mixing, because the ground-based measurements are sometimes very difficult to apply directly to the imaging itself. But because we've got these ground-based measurements at a much more refined temporal interval, we can model things more effectively. And here's an example of our initial analysis. Here we've used a technique called band depth normalized by area, and we've identified that we have a maximum contrast within the region of 1.58 nanometers, and that ties in with a lignin absorption feature, which is part of the plant process. So we're showing a relative contrast response due to different physiological changes in the plant. Finally, we're an open science project, and this means that we will be putting all of our observations out into the public domain as soon as it's practical. So this means that other researchers or members of the public can access the data, the information and knowledge. It can be shared more effectively. It reduces the barrier to access scientific data. So if any of you want to look at what we're doing, or to start to mess around with algorithms or play with the data is there. And there's a whole range of benefits for us, which are summarised in this information here. Thank you very much indeed.